In the last lecture, what we were discussing was confidence interval, setting up of confidence intervals for certain type of linear combinations of the elements of the mean vector mu coming from a multivariate normal population. So, we had an underlying multivariate normal population, multivariate normal m dimensional with the mean vector mu and a covariance matrix sigma, which was actually assumed to be positive definite. And we had the following discussion that we were looking at these linear combinations ai prime mu quantities for I equal to 1 to p, where p is less than or equal to m, and we were trying to find out a simultaneous joint confidence interval for all of these linear combinations such that the coverage is at least 100 into 1 minus alpha percent. What we had seen in the last lecture was we had taken a specific example of these linear combinations ai prime mu terms, and we had taken those linear combinations as p components mu 1, mu 2, mu p. Without loss of generality, we take the first p of them mu 1, mu 2, mu p, and we were looking at two different possibilities, two different cases under which such simultaneous joint confidence intervals may be derived. Now, the first case what we had seen in the last lecture was that we had assumed that sigma is a diagonal matrix, so that the components of x multivariate random vector becomes independent, and under such circumstances we had derived the simultaneous confidence interval of covering mu 1, mu 2, mu p, and we had also the discussions about that. Let us now look at the more general case, which is the case where case 2, where we have these. Suppose this sigma is not a diagonal matrix, that the more general case rather is not diagonal matrix. So, we do not have independence of the components of x's x1, x2, xp, and hence we cannot also infer about the independence of the components in x bar, that is x1 bar, x2 bar, xp bar or xm bar to complete it. They are not necessarily independent, they are not independent actually. So, sigma is not a diagonal matrix. Under such a circumstances, what is used is what is referred to as the Bonferroni's method for construction of this simultaneous confidence interval for this linear parametric functions or the linear transformations ai prime mu terms for I equal to 1 to up to p. Now, we may recall that for events E1, E2, EP, P events, probability of intersection of EI terms I equal to 1 to up to P, this is greater than or equal to 1 minus summation I equal to 1 to up to P probability of EI complements. Now, this is equal to 1 minus summation I equal to 1 to up to P 1 minus probability of these EI terms. So, that this is equal to 1 minus P plus summation probability EI terms. Now, suppose we take, if we take this probability of EI to be equal to 1 minus alpha by P, then what happens in the above inequality is the following. Then probability of intersection of these EI terms I equal to 1 to up to P, this is greater than or equal to, now here we have summation I equal to 1 to up to P. So, what we will be having is 1 minus P plus summation I equal to 1 to up to P 1 minus alpha by P. So, that this term is equal to 1 minus P plus P minus alpha. So, this P term cancels out, and what we will have, this is equal to 1 minus alpha. So, this basically is derived from Bonferroni's inequality, and hence the name of construction of the simultaneous confidence interval is what is given as the Bonferroni's method. Now, when we have seen that for such P events E1, E2, EP, intersection of this is greater than or equal to 1 minus alpha, if we can choose probability of EI to be equal to 1 minus alpha by P, this leads us to the thought of construction of the simultaneous confidence intervals such that the coverage would be greater than or equal to 1 minus alpha. So, if we can choose these EI events as the events that mu I is belonging to a certain random interval such that the probability of each one of those EIs, if we can make that equal to 1 minus alpha by p, then we will be able to achieve the simultaneous coverage of such linear functions. Here we have just mu 1, mu 2, mu p in terms of simultaneous confidence intervals with a coverage of at least equal to 1 minus alpha, right. Now, if we take that particular clue, consider confidence intervals for each of these mu i's as say x I bar minus plus t n minus 1 alpha by 2 p, this multiplied by s I by n. So, this is for I equal to 1 to up to p. So, if we take a confidence interval of this particular form x I bar, so the lower confidence limit is x I bar minus t n minus 1 alpha by 2 p into root over s I by n, and the upper confidence limit is x I bar plus t n minus 1 alpha by 2 p root s I by n. So, if we take that, then if we define this E I event to be the event that mu I is belonging to the random interval, that this is x I bar, this is x I bar minus t n minus 1 alpha by 2 p, this into under root of s I by n to x I bar plus t n minus 1 alpha by 2 p into under root of s I by n. So, this is an event that mu I is belonging to this random interval. So, this would imply that probability of this E I is going to be equal to what? That mu I is belonging to this particular interval. This in terms of the t distribution is what is going to lead us to 1 minus alpha by p. Now, here of course, where we have this t n minus 1 alpha by 2 p is such that probability that a t distribution on n minus 1 exceeds this point t n minus 1 alpha by 2 p point. So, the probability that a t distribution exceeds this given point, this is going to be equal to alpha by 2 p. So, we will have alpha by 2 p to the right of this, alpha by 2 p to the left of negative of this particular term. So, the area on the right and the left of the positive t alpha by 2 p and to the negative of alpha by 2 p would just sum up to alpha by p, and hence the area between them, this is what I am trying to convey. So, if this is the t distribution PDF, we have a point here which is our t n minus 1 alpha by 2 p. So, the area to the right of this is alpha by 2 p. It is a symmetric distribution, and hence the area to the left of negative of t n minus 1 alpha by 2 p, this area to the left of this point is also alpha by 2 p. So, the two add up to alpha by p, and then the area between these 2 points is 1 minus alpha by p, and that is what we have area, because that is what is going to be given from this expression out here. So, this would imply that if we have such random events EIs which are basically coming from the respective confidence intervals for the mu I parameters, this would imply that probability of these intersection of EIs I equal to 1 to up to p. So, these are basically the events associated, EI is the event associated with the mu I component, and then this intersection probability is going to be greater than or equal to 1 minus alpha, as what we had derived out here, that if we can choose probability of EI to be equal to 1 minus alpha by p, then we will have probability of intersection of EI to be greater than or equal to 1 minus alpha, and we have chosen actually those random intervals in such a way. For each of these parameters mu I, we have chosen the random interval in this particular manner, and so that we will be having probability of each of these EI events to be equal to 1 minus alpha by p, and then from that we will be having probability of intersection of EI to be greater than or equal to 1 minus alpha. So this basically is going to this is giving us the simultaneous confidence interval. So this E1, E2, EP gives the simultaneous confidence intervals for this parameters mu1, mu2, mu-p with confidence level of at least 1 minus alpha. So we have ensured that with such random intervals we are able to have a coverage of at least 1 minus alpha. So this is what it turns out to be. Now one can actually have more general approach to constructing such confidence interval. So more generally we can actually look at, now note that when we are looking at these EI terms, EI events here for the parameter mu I, what we are doing here is that we are choosing this EI sets in such a way that probability of each of the EIs, so this probability of EI equal to 1 minus alpha by p, this is true for every I equal to 1 to up to p. So we have the probability of coverage of each of these mu i's to be exactly equal to 1 minus alpha by p for all the i's. Now we can actually play around with this probability, because not all mu i's may be equally important to us. Some of the mu i's may be more important to us, some of the EI's may be some of the mu i's may be less important to us, and hence we can take care of that even using this particular approach. So what we can do is that more generally let EI be now the set that mu I belongs to interval similar to what we have considered, but we will actually not be having alpha by 2p at all for all the mu i's. We can make this as alpha I by 2, so that it depends on mu I, this level of error depends on the particular mu I that is chosen here. This into SII by n, this is same as what we had previously. This is xi bar plus Tn minus 1 alpha I by 2. Now this Tn minus 1 alpha I by 2 has a similar interpretation as to what we had noted out here, that Tn minus 1 alpha by 2 p is the upper alpha by 2 p cutoff point of a t distribution on n minus 1 degrees of freedom. So similarly here this Tn minus 1 alpha by 2 point is the upper alpha I by 2% point of a t distribution on n minus 1 degrees of freedom. So that this now turns out to be that this is SII this divided by n. So this is what is the random interval now we are considering. Now what would happen here, what is the probability of such EI terms? Now alpha 1, alpha 2, alpha p actually varies with respect to mu 1, mu 2, mu p. So the probability EI by the similar logic would be 1 minus alpha I, right. So this is the probability of EI, because we have the cutoff point here alpha I by 2% point. So alpha I by 2% point is on the right, alpha I by 2 is on the left of minus Tn minus 1 alpha I by 2, and hence the total area to the right of Tn minus 1 alpha I by 2 and the area to the left of minus Tn minus 1 alpha by 2 would be alpha I, and hence the area in between the two cutoff points would be 1 minus alpha I, and this is what is thus giving us this particular quantity. This is for I equal to 1 to up to p. Now alpha 1, alpha 2, alpha p are different with a restriction. Now with this setup with this general setup, so to say, probability of this intersection of EI events, that what is given from the Bonferini's inequality is what we had derived earlier, that was 1 minus p plus probability of EI. So, what does this now lead us to? 1 minus p plus summation probability of EI terms I equal to 1 to up to p. So, with probability EI given by 1 minus alpha I, we will have this to be equal to 1 minus p plus summation I equal to 1 to up to p. 1 minus alpha I is what we are getting. So, it is 1 minus p plus p minus summation alpha I equal to 1 to up to p. So, this is nothing but 1 minus summation of these alpha I quantities. So, if we take summation alpha I equal to 1 to up to p equal to alpha, the desired level of error. So, if we take this summation alpha I, then we will have probability of this simultaneous coverage, that is intersection of these EI events, this is going to be greater than or equal to 1 minus alpha. So, this is the required thing or the desired thing what we are trying to ensure, that the joint coverage of all these parameters mu 1, mu 2, mu p, which are given through these EI events, random events, we will have this joint coverage to be greater than or equal to 1 minus alpha if we restrict ourselves to summing these alpha I quantities to be equal to alpha. So, this actually allows us to control the error rate of the respective mu I components in the way that when we are looking at a particular mu I, probability that mu I lies in that particular confidence interval is 1 minus alpha I. So, lower the value of this alpha I here, higher is the coverage for that particular mu I. Higher is the value of alpha I, lower will be this EI. Now, this alpha I is of course lying between 0 and 1. So, with that restriction we are now playing around with alpha 1, alpha 2, alpha p. These are corresponding to the mu 1, mu 2, mu p terms, and hence what we are now looking at is to control the error rate with respect to various mu i's, and then we will have alpha I values lower for the mu i's which appear to us as more important, and hence we can do that quite easily when we have this particular general setup. So, this will imply that this allows us to control the error rates alpha 1, alpha 2, alpha p with this summation alpha I equal to 1 to p equal to alpha, which is the desired level of significance. This is regardless of the correlation structure, the underlying correlation structure which is given by the sigma matrix. Furthermore, we have a flexibility actually. We have a flexibility of controlling the error rates which are alpha i's, error rates of a group of important parameters, right, because we can make alpha I corresponding to a particular mu I which is of say more importance to us, and then we can have that being compensated by some other mu I which is not that important, and hence we can thus look at having higher coverage for the parameters of more importance and comparatively lower coverage in the simultaneous confidence interval setup to have been attached to other type of contrasts. Now, this particular example, when we had considered to start with that we are looking at a particular type of linear combination AI primes, where AI vector was having 1 at the ith position and 0 at all other locations. So that had led us to constructing the simultaneous confidence interval for mu1, mu2, mu_p. We had considered two different cases, case 1 and case 2, case 1 where sigma was a diagonal matrix, and case 2 where sigma was not necessarily a diagonal matrix, and have obtained actually all those simultaneous confidence intervals. Now this approach can be extended for any linear combining vector AI, any type of linear combining vector, and hence this method can easily be extended for such situations. Only thing is that here the distributions are going to change. In place of xi bar we will be having AI prime x bar terms, and the corresponding variance term will also get replaced. In place of Sii we will have whatever will be the variance of that AI prime x bar terms, right. So the next thing that we are going to look at is t-square confidence intervals. It's another important thing about the Hotelling's t-square statistic. These are t-square confidence intervals. What are these? Now note that we have proved a result in the way that supremum over A of n times A prime x bar minus mu whole square, this divided by A prime S A. We had in the last lecture obtained what is the supremum of this particular quantity, and this was shown to be equal to t square, right. So this is what a given result is. So this would imply that t square less than or equal to some c square. This would imply, so if we have t square less than or equal to c square, this would imply that this n times A prime x bar, let us split it, A prime x bar minus A prime mu whole square, this divided by A prime S A, this term is also going to be less than or equal to c square. This is going to be true for every vector A belonging to R to the power m if x is m dimensional. So from this result here, what we can infer is this particular line. So in other words, because t square is the supremum of this particular quantity, and t square being less than or equal to c square would imply that these quantities will be less than or equal to c square for every possible value of A belonging to here R to the power m. That is, we can write this in the following way, that we will take this A prime x bar outside, this is minus c times under root of A prime S A, this divided by n. This is going to be less than or equal to, we are actually looking at type of confidence interval type scenario, and hence we are expressing this, because once we have this less than or equal to c square, we will have the absolute value of this being less than or equal to c, and hence we will have that to lie between minus c and plus c, and then we will be having the expression that I am writing now. So this is going to be given by this A prime S A, this divided by n. So the under root of course is both in the numerator and in the denominator. This is going to be true for every vector A belonging to R to the power m. Now we further know that this t square by n minus 1 into n minus m by m, we have seen this time and again, this follows an f distribution m n minus m degrees of freedom. So this would imply that probability that this t square by n minus 1 into n minus m by m, this less than or equal to f m n minus m alpha, so that this is the upper alpha percent cutoff point of this f distribution. So this is going to be equal to 1 minus alpha. So if that is the case, we will be able to write this t square less than or equal to m times n minus 1, this divided by n minus m, this times f m n minus m times alpha, this is equal to 1 minus alpha. Now, why have we written this particular fact and reduced it in this form? What we are trying to see is that what is the probability of such an event, that t square is less than or equal to c square, that we desire that to be equal to 1 minus alpha, and hence if we choose c square to be equal to this particular point, which is m times n minus 1 by n minus m into f m n minus m alpha, if this is chosen as c square, then probability that t square is less than or equal to c square is equal to 1 minus alpha, and hence that would ensure that the joint coverage of such events for every value of a, that is going to have a coverage equal to 1 minus alpha, because t square less than or equal to c square implies that a prime mu for every mu belonging to r to the power m actually has a coverage equal to the coverage of this particular event, which is 1 minus alpha. So, we will take this c square to be equal to that constant what we had, m into n minus 1 into n minus m, this into f m n minus m times alpha, right. So, this gives intervals that would contain this a prime mu term for every value of a with probability equal to 1 minus alpha, with probability 1 minus alpha. This gives intervals that would contain this, which is of the form that is given from this previous discussion, that we are going to have this now with a c which is given by the under root of this particular quantity, we will have the coverage equal to 1 minus alpha. So, this interval now is given by this a prime x bar, this minus under root of this entire quantity, which is m n minus 1, this divided by n times n minus m into f m n minus m alpha, this into a prime s a. This is the lower confidence limit for that particular a prime mu, and the upper limit is a prime x bar, this plus the same quantity out here, which is m into n minus 1, that divided by n into n minus m, f m n minus m a prime s a. So, this basically is going to give us that simultaneous confidence interval. So, this interval will contain a prime mu for every a simultaneously. So, this leads us to another type of simultaneous confidence intervals, which are termed as t square confidence intervals. The reason why they are called t square confidence intervals is that this cutoff actually f m n minus m alpha, this term here, along with the constant m n minus 1 and n minus m, this is what is the cutoff, basically this particular term here, that is given from the t square Hotelling's t square distribution. So, that brings us to the end of this particular section. What we are now going to see is an important application of Hotelling's t square statistic, which is called the profile analysis. Now, profile analysis is an important applied multivariate tool wherein we look at the following things, and let me first introduce. What we are now going to see is profile plot and profile analysis. Now, what is the setup of this particular type of analysis? We have two groups. Group 1, this is a p dimensional population, p or m whatever, p dimensional population, and we have a group 2 second group which also is a p dimensional population. Now suppose we have n1 observations from this group 1, and similarly we have n2 observations taken from group 2. Now what we are trying to see is that suppose we assume that the group 1 is characterized, group 1 in the population is characterized by a mean vector, say eta, which is equal to eta 1. There are p characteristics in that population. It is a p dimensional population, and hence this is eta 1, eta 2, eta p. And similarly group 2 is characterized by a mean vector which is given by, say, nu. This is equal to nu 1, nu 2, nu p, say. So these are the two mean vectors characterizing these two populations, say. Then we define the profile plot of these two groups as the following. So this is a small definition out here. The profile plot of the group is defined to be the graph. It's very simple actually. Let me first write the definition obtained by joining the points I eta I and I plus 1 eta I plus 1, or we can similarly say that it's I nu I and I plus 1 nu I plus 1. So this is what is called the profile plot. What it is actually, the definition can be given in this way. The plot actually is nothing but the following, that what we have here, these are the p dimensions, say 1, 2, 3 and so on. So these are the p dimensions in the two populations. Now here we just plot what are the means corresponding to these groups. So this point is 1, say for group 1, this point is 1 eta 1. So we join 1 eta 1 with 2 eta 2. Suppose that particular mean point is here. So we go on joining that like this. So this is just the point obtained. So this point would be what? This point would be, suppose this is for group 1. This is suppose the profile plot for group 1. Then this point here is nothing but p eta p. This point, the starting point here is 1 eta 1 and so on. This point is 2 eta 2 and so on. So we are joining consecutive points I eta I and I plus 1 eta I plus 1, and this basically is a simple graph which is called the profile of the group 1. Similarly, one can draw a profile of the second group. Say suppose that profile is given by this. It can be of any shape, right. So this is similarly the profile for group 2. So this is group 1 profile, this is the group 2 profile. Now another profile plot can be of the following nature, that it is like this, another profile plot. So this is also a profile plot. Now thus in profile analysis we look at what type of analysis, what type of questions are of interest when we have two or more such profile plots. Now this is for two groups that I have two profiles. If we have k groups, then we will have k such profiles drawn on one paper, one graph here, and hence we will have that figure to give us an idea about the profile of k groups under consideration. This is just a simple thing to have two such groups. Now this profile analysis has got immense applications in the field of market research, clinical trials, applications in the areas of clinical trials, biostatistics, market research, and various other areas. Now the point to be noted here is that although we are saying that this is the profile plot of group 1, this is the profile plot of group 2, similarly this will also be characterized by some characterizing feature, group 1, group 2, group 3 and so on. Now such profile plots are actually unknown to us, because for all practical purposes these are the means in the respective populations. So this eta 1, eta 2, eta p is characterized by the mean vector in the population. Similarly nu 1, nu 2, nu p is the mean vector which is characterizing that second group of population, and hence these are unknown quantities, and hence the actual shape of these profile plots are unknown to us. Since we have the exact structure of these profile plots unknown to us, because the respective group means in the populations are not known to us, that is eta 1, eta 2, eta p, or nu 1, nu 2, nu p, all of them are unknown quantities, and hence this exact shape of the profile plot is unknown to us. What is done is to look at the sample profile plot, because we have n1 observations taken from the first sample, n2 observations taken from the second population, the n1 observations from the first population, n2 observations from the second population, and hence using those n1 and n2 populations one can obtain the sample means, sample mean random vectors for the two groups, and then the sample profile plot is obtained. The sample profile plot is obtained by replacing the population mean components by the respective computed sample mean components. Now this is what we can actually see, because from n1 observations we will be able to get to x1 bar. I say this is the mean vector corresponding to the first population. So this will have the elements as x bar first population, first component, and similarly this would be x p bar first population, pth component. Similarly from n2 observations from the second population or the second group, we will be having x2 bar vector. This is computed from the n2 observations coming from the second group, and this will have the components as following, that this is xp2. Now using these values now and thus replacing these eta i's by the corresponding x1 I terms and nu i's by this x bar 2 I terms, will be having the corresponding sample profile plots. Now given that we have got in the unknown population profiles of this nature, profiles of this nature or some other nature, there are certain points of interest in profile analysis in which one is interested in. They are the following. In profile analysis we try to address the following points. in profile analysis we answer the following questions. Number 1 is that are the profiles similar? Are the profiles of the groups actually are the profiles similar? Similar in terms of they being parallel. This is the first type of point of interest in profile analysis. Like here, these two group profiles does not appear to be similar in the sense that they are not parallel. On the other hand, if you look at group 1 and group 2 profile on this profile plot, they appear to be parallel, although there is a divergence here, but we need to see whether this divergence from parallelity is statistically significant or not. So that type of things are what we are going to answer. Now the second type of question that is of interest, assuming that the answer to one is in the affirmative, assuming that the answer to one is in the affirmative, that is we answer this particular question that they are similar or parallel, we say that well they are. If they are, then we are further interested to see that whether these two parallel profiles are coincident or equal profiles. So once they are in the affirmative, that is profiles are parallel, are they equal, that is are the two profiles coincident, right. So once we assume that they are parallel, we look forward whether they are actually equal or there is a significant difference between these two similar parallel profiles. Now the third point of interest, once we have accepted this first type of hypothesis that we say that well the profiles are similar, that is they are parallel, and next also we say that well they appear to be equal, coincident, and the divergence from the two being equal is not statistically significant, then the third type of question that we usually try to answer is that whether the common profile is a level profile. Level profile in the sense that we have got all the components common in the, now the first is eta for the group 1, the second is nu for the second group. In the first one we are looking at the two profiles and then seeing whether the two profiles are parallel or not. Once we accept the fact that they are parallel, then we move on to see whether the two parallel profiles are actually coincident profiles, that is there is not significant difference between the two profiles of the two groups. If we actually accept that particular question or rather that particular hypothesis also, that the two profiles actually are equal, that is there is a common profile, then we try to look at the third point of interest, whether the common profile of the two groups is level profile, level in the sense that all the components are same, right. So that the third point of interest, let me write it first, then I will explain, that assuming that the answers to 1 and 2 both are in the affirmative, is the common profile, because that is what we have accepted in 2 is the common profile level, that is are all the means equal to some constant. So that is the third type of question that is usually addressed to in the profile analysis. I hope this is clear. What is the sequence of the testing, or rather the sequence of answering these questions. First we look at this particular question to be answered, Now, if at this particular stage we say that, well, the profiles by the statistical testing procedure that we are going to frame, the two profiles does not appear to be similar or parallel, then we will not proceed further. We will not proceed to check whether they are equal or coincident, because if the two profiles of the two groups are not even parallel, then there is no question of looking at them being equal or coincident. So, if the first question is answered as yes, that the profiles appear to be similar, that is, they are parallel and the divergence from parallelity is not statistically significant, then what we do is we proceed to this second question. If the answer to the first question is in the affirmative, that is, they are parallel, we check whether they are equal or coincident profiles. Now, if at this particular point, after acceptance of the parallelity of the profiles, we come here and we say that, well, the profiles may appear to be parallel, but they are not equal. If we answer in that way, that they do not appear to be equal, then we do not proceed to test or to answer this particular last question, whether they are having a level profile, because if they are not at all equal, then there is no question of having a common profile of the two groups, and hence we do not move on to the third question here. Now, if the answer to this second question, that whether the profiles are equal or coincident, once again is answered in the affirmative, that we accept first that the profiles are similar, we then accept that the profiles are equal, is a level profile. Now, this is all in literature terms. We need to translate this three type of questions in statistical terms. What are these questions in statistical terms? In statistical terms, we are actually looking at the following. The first question, that the profiles are similar or parallel, is going to be answered through testing of this particular hypothesis. We will frame an hypothesis which will say that this eta k minus nu k is equal to eta k minus 1 minus nu k minus 1. This is for k equal to 2 to up to p, whether this hypothesis is acceptable. Now, how is this going to be related with the parallelity of the profiles? Because if you look at a profile plot, these basically, so the difference, so we will have this as the profile of group 1, this as the profile of group 2. So, we take this point as eta 1, this point as nu 1. So, this is the difference eta 1 minus nu 1. So, this is the difference, and this is the difference eta 2 minus nu 2. Now, if all these differences are same, then we will have the two profiles naturally to be parallel, and hence when we are trying to answer the question that the profiles of the groups are parallel, we are framing or rather translating that particular question in terms of statistical hypothesis testing, in terms of this H01 hypothesis, that eta k minus nu k is equal to eta k minus 1 minus nu k minus 1. This is for every k from starting from 2 to up to p. So, all the differences what we have as this eta 2 minus nu 2 is equal to eta 1 minus nu 1, that is equal to eta 3 minus nu 3, and so on. So, all those differences in the profile, they are all same, against that they are that all of them are not same. Now, this hypothesis also one sometimes writes it as eta k minus 1. This difference is equal to nu k minus nu k minus 1. This is in the equivalent form. So, this is the first hypothesis that is going to test the parallelity or similarity of the two profiles. Now, the second hypothesis is what we are going to frame, which is going to look at equality or coincidence of the two profiles, given that the first hypothesis is accepted. So, the second type of hypothesis that we are going to frame for testing equality or coincident nature of the profiles is that is H naught 2, that we will have equality which is eta k equal to nu k. This is for k equal to 1 to up to p. Is this hypothesis acceptable or not? Now note that this is equivalent to H naught 2 prime, which is going to be summation eta k. This is equal to summation of these new k terms, and an important thing to be noted is here is that we will only test H naught 2 if H naught 1 is accepted. H naught 2 to be tested only if H naught 1 is accepted, then only this equality of the profiles make any sense, otherwise not. So, if at the first stage H naught 1 is rejected, that we say that the two profiles are not similar or parallel, then we will not proceed further for testing H naught 2. Now, under the situation that H naught 1 is accepted and all these differences that we were talking about, which actually leads us to parallelity acceptance of the profiles, those differences being equal, this hypothesis that eta k equal to nu k would be equivalent to this summation of eta k to be equal to summation of nu k. So, this is basically going to take care of this particular hypothesis, this type of questions. This statistical hypothesis H naught 1 is going to take care of this question number 1. What about question number 3? Question number 3 is what is looking at that answer to 1 and 2 are in the affirmative is the common profile level. So, in terms of this statistical hypothesis, how we are going to frame? We are going to frame it in the following way, that if H naught 1 and H naught 2 sequentially in that particular manner are accepted, then we move on to test H naught 3 hypothesis, which is going to be the hypothesis which is going to actually answer the last question, that is about that level profile thing. So, we are at the last question here. We will have the last question being answered in terms of the following hypothesis H naught 3, which is going to be that hypothesis which is going to test that eta 1 equal to eta 2 equal to eta p, this is equal to nu 1 is equal to nu 2 is equal to nu p, right. So, this is whether this hypothesis is acceptable or not. So, these are sequentially the 3 type of hypothesis, whether this is acceptable, that is first we answer. Next we answer whether this H naught 2 is acceptable, and this is to be H naught 2 is to be tested only if H naught 1 is accepted. Now, similarly, when we talk about H naught 3, it is looking at whether all the components eta 1 equal to eta p, these are equal. Now, this H naught 3 to be tested, H naught 3 is to be tested only under the situation that both H naught 1 and H naught 2 are accepted. So, only under such a situation we are going to test this H naught 3, and that H naught 3 under the situation, under the condition that both H naught 1 and H naught 2, remember H naught 1 is the hypothesis for testing similarity of the profiles, H naught 2 is the hypothesis for testing equality or coincident nature of the profiles, and H naught 3 is the last hypothesis which is going to test whether the profile is a level profile, that all the components are basically same. And the sequencing of the testing is that first H naught 1 has to be tested. If H naught 1 is rejected, we stop at that particular point. If H naught 1 is accepted, then from after testing H naught 1 we move on to testing H naught 2. If H naught 2 is accepted, we move further to test H naught 3. If H naught 2 is rejected, we stop at that particular point and we say that, well, the profiles were parallel, but they are not equal. If all the 3 hypotheses H naught 1, H naught 2, H naught 3 in that order are accepted, we will say that the profiles first are parallel, the profiles next are equal, and the profiles, the common profile of the 2 group is level profile. In the next lecture we are going to see how these H naught 1, H naught 2 and H naught 3 are tested using a Hoteling's t-square statistic. We are also going to see some numerical examples of looking at how this profile analysis is going to be carried out. Thank you.